Hey everybody, it's Mr. Ross again. We're going to be talking about the periodic table and periodic trends today. Before we get started, I want to give credit again to Mr. Forrest, who works over at Pickerington North High School, for lending these notes to me. As we go over these, fill in the blanks. I'm going to try and stick to the script as much as possible. But before we get started here, um, I just wanted to let you know that this is going to be a very illuminating experience for you to help you understand what the periodic table actually is. I have a lot of students in the past who they come into me in integrated science and they have like a bunch of the elements memorized on the periodic table. And I said, that's great. How do you do this? And then they have no clue. What I want you to understand is the periodic table is actually, it's a tool and it's put together in this very beautiful way, and we're going to talk a little bit about that today. But it is not just something to be memorized. You have portions of it that you can memorize that are going to help you a lot more than just memorizing that, like, oxygen is number 8 on the periodic table. That's helpful to a degree, but remember, it's more of a tool. It's not just like a memorization thing. We're going to take a look at your guys' notes. So we've already talked about the fact that atoms have electrons on their outer section. This is kind of the model that we have right now for our atoms. And again, this looks very similar to the Bohr model that you guys saw earlier. The protons are the positives, neutrons have no charge, are the white ones, and electrons are kind of orbiting outside on these different shells. And we've talked a little bit about this, but also neutral atoms can gain or they can lose electrons, and sometimes they become charged. Atoms that have a charge are called ions, I-O-N-S, like ion you, okay? Normally the outermost electrons are the ones that are gained or lost. Why does this happen, though? We're going to talk about this. This is our lead-in as we get talking about the periodic table. Well, these electrons don't just fly around in random places. They exist in these shells, and you guys have seen this. So here's one shell. It holds 2 electrons. This is another shell that currently has 4 electrons. Sometimes those are called orbits, by the way. In our planetary model, and again, we call it a planetary model because you have these things orbiting around this nucleus. This was developed by Niels Bohr, again. Each outer shell, which is an energy level, so each of these shells is an energy level, is most stable when this outer shell has 8 electrons, or 8 outer electrons. So if you look at this current one, it's not very stable because it's only got 4. This idea that we are most stable when our outer shell, or the valence shell, has 8 electrons is called the octet rule. So we would ideally want 4 more electrons in this outer shell for this thing to be stable. So there are 2 exceptions to that, and we're going to take a look at them on the periodic table real quick. Helium and hydrogen are 2 exceptions because they can only hold 2 electrons because they will only ever have 1 shell. Hydrogen and helium are in this first period, and the first period can only hold 1 shell, and 1 shell, the first shell, is always only going to be able to hold 2 electrons. So I want to make note real quick, this model of the atom is not the current best model that we have. It's just what we're learning now as you guys get your basics for chemistry. As you take higher levels in high school and college, you'll learn different models besides this planetary model. So we're going to take a quick look at this element right here. All right, N represents just the nucleus, so we're not telling you how many protons there are, so you can't necessarily look it up like that. But you can see that it has 3 shells. It has one shell that has 2 electrons, another shell that has 8 electrons, and then this third shell only has 7. So 2 plus 8, which gives you 10, plus 7 more, which gives you 17. So which atom are we showing on there? If you are able to use your periodic table well, you take a look and you see that the element that would normally have 17 electrons is going to be the same element that would normally have 17 protons. So let's find 17 on the periodic table, because number 17 is the one that is going to have 17 protons, and therefore it would have 17 electrons. So that element that we just showed you would have been chlorine. Okay. Those outer electrons that we looked at, and again, I'll show you real quick. These outer electrons are called valence electrons, and they are one of the most important things that we need to understand the periodic table and also how elements react with one another. Since valence electrons are the only ones that really interact, they either leave the atom or they come back to the atom. So again, leaving the atom, or they might have electrons that come to this atom. They're the ones that are going to be important for chemical reactions and bonding, which we'll talk about later. So to make predictions about the periodic table and different chemical reactions that we're going to have, the real basic thing that you need to know is that octet rule. Again, the octet rule says if we have 8 electrons in our outer shell, we're stable. If we don't, we're not stable. So, and in nature, things usually like to move to a level of stability. So, the periodic table that we have today looks like this. All right. We're very familiar with it by now. We've seen it a bunch of times. But it was originally developed by this guy named Dmitry Mendeleev in 1869. He put the elements in rows based on their atomic mass, and then he noticed that each column of elements had very similar chemical properties. So he noticed, for example, he had this first row, and then the second row that he had lithium, beryllium, boron, carbon, nitrogen, oxygen, and then fluorine. And he noticed that they all had very, very similar properties in them. So, what he, pardon me, he also noticed that if you go down in a group, they have some similar properties. The property that's mainly, I guess, similar in a row is it's got a, so, Mendeleev, what he did, though, is he left some different blank spaces. You can see a couple of them on here, like right here. And he left those blank spaces because there were breaks in properties and masses, and he predicted, based on those breaks, that there was going to be some elements that would be discovered in the future. And even if you look on here, our modern table in group 5A, which is where my cursor is right now, that one normally has helium in it, and they didn't have it back then at that point. So he was definitely right. We discovered a lot more elements. But also, just real quick while we're on this, if you look at his table, group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8. This is very different from our modern periodic table, because if you take a look on the modern periodic table, we've numbered it all the way 1 through 18. That's because we have these 10 groups that are the transition metals, not the transmission metals. All of these things in his time were incorporated in a slightly different way on his periodic table. But again, if you look at group 1, group 2, and then 13 becomes 3A, 14 becomes 4A, 15 becomes 5A, 16 becomes 6A, 17 becomes 7A, 18 becomes 8A. If you remember that, that's going to help you with this octet rule as we go over it. Okay. Our modern periodic table is not based necessarily on the mass. It's based on the atomic number, but the atomic number is equal to the number of protons in the atom's nucleus. So it is still pretty similar. Again, if you look at his table and then you look at the periodic table that we have right here. So, characteristics of our periodic table today. The periodic table is arranged in rows that are called periods. Okay, so you can see here, row 1, row 2, and again, those are called periods. So we would say like period 3, that's the one that starts with sodium, then magnesium, then aluminum, silicon, phosphorus, all of those ones. So each of these periods represents a different shell of electrons. So if you look at this first period, it will have one shell of electrons. And remember, the first shell can only hold 2. The second period can hold up to 8 because it has 2 shells. Okay. The third period will have 3 shells, and remember that outer shell can hold up to 8. The second shell can hold up to 8. The first one can only hold up to 2. And that's just kind of how it is going down there. and we're only going to deal with periods 1, 2, and 3, just so you guys know. Note that for this atom with a fourth shell, so if there's an atom that is in the fourth period, it would have 4 shells. Its valence electrons only exist in its outer shell. So the ones, like I'm going to take a look here at scandium real quick. Whoops. Scandium, when you look at it, has 2 valence electrons. These 9 that we see here, we're not going to worry about that. You guys don't need to worry about it at all. Its valence electrons are going to be the ones that are going to be important to us. And so if you look at calcium, it has 2 valence electrons. If you look at gallium, which is in group 3A, remember, gallium has 3 valence electrons. Germanium in group 4A has 4 valence electrons. Are you guys seeing the pattern here? Whichever group you're in, that tells you how many valence electrons you have, okay? There are different regions on the periodic table, and right now you can see them color-coded. If you look at the group 1A, 2A, the A groups, you notice that their Roman numeral is going to match the number of valence electrons. That's what I just said in each of the elements in that group, okay? Now looking at some of the bigger patterns. If you look on this periodic table, okay, the metals are all of the things that we currently have that are not gray on there. So kind of the greenish, the tannish color. The lanthanoids are kind of a peachy, creamy. We have the actinoids. When I scroll down there, actinoids are going to be like a purplish color. Alkaline earth metals are yellow. Alkaline metals are orangish. All of those things are metals. And this is the largest group of elements. They usually like to donate or lose electrons, and they are to the left of this thing called the staircase. I'm going to show you guys the staircase over here. There's this magical line a lot of times that you'll see that goes, follow my cursor down, and it's over one, and down one, and over one, and down. And it just looks like it's a big staircase. So we talk about that staircase a lot. It's just a reference point for us, and there's some weird stuff that happens around those areas. So metals are to the left of the staircase, so all this stuff over here, with the exception of hydrogen. But hydrogen acts like a metal under some pretty weird conditions, like in the sun and stuff like that, but you don't have to know that. Metals are usually really good conductors of heat and electricity. They're shiny. They usually are malleable. They can bend without breaking. Most of them are solid at room temperature except for Hg, which is mercury. Okay. Mercury is a liquid at room temperature, and mercury is right there, number 80 on the periodic table. And most metals are ductile, which means they can be pulled out into long wires and things like that. Now, moving on to the nonmetals. The nonmetals are to the right of the staircase. That would be the things in green here, the halogens, which is group 7A, and then the noble gases, which is group 8A. Okay. They tend to want to gain electrons. So all of these non-metals that I have highlighted, they usually like to gain electrons. Oh, and don't forget hydrogen all the way at number 1. Okay, I forgot about that. They do not conduct electricity or heat very well. They're usually brittle, and most of them are actually gases at room temperature. There are a few exceptions to that as well. Not all of them are gases at room temperature. Then we have this funky little group called the metalloids, and those are kind of like the light green ones that I have highlighted right here. The metalloids touch the staircase. Not everything's touching the staircase is a metalloid, so like you can see aluminum. Aluminum would be touching the staircase right here. It's right underneath the staircase, but it is a metal. It's not a metalloid. Metalloids are kind of this in-between. They have properties of metals. They have properties of non-metals as well. They are usually really good semiconductors, which is important for electrical devices, and they can usually gain or lose electrons. So they're pretty interesting with chemical reactions. So now, in your notes, we have some different pictures, and we're going to take a look at those pictures real quick. If you look at there, remember N is going to represent the nucleus. We have an element that has, if you count it up, 7 valence electrons. So that should right away help you narrow down which element this is. Okay? If it has 7 valence electrons, use your A groups and figure out where it would be. It's not going to be in group 1A or 2A or 3A or 4A or 5A or 6A. If it has 7 valence electrons, it's going to be in 7A, okay? Which again is 17 on the periodic tables that we have today. So it's going to be one of these different things going down here. If you count them all up, there are a total of 17 electrons though. So boom, 17 electrons is going to be chlorine. Okay, so that first element is chlorine. Take a look at the other element that we have. It has 2 valence electrons. So if I use, again, my knowledge of the periodic table, I could figure out it's going to be in group 2A. So it's going to be something in here. And if I count up all my electrons, I have 2 on the inside, 8 on the second shell, 2 on the outer shell. That would be magnesium, total of 12 electrons. Now, I just told you that all the stuff that you would have to go through to figure out that that was magnesium. But if you've been paying attention, there's other tricks to how to find these elements really quickly. If you saw that it just had 2 valence electrons, again, you would know that it's going to be in group 2A. So this one that I've highlighted right here. But the other thing that you can look at is if it has 3 different shells, then you know it's going to be in period 3. So in this row. You can kind of do the across and then the down and kind of figure out where they meet. So it's going to be in this group, but it's going to be in the second group, or sorry, it's going to be in this period 3 because it has 3 shells, and it's going to be in group 2 because it has 2 valence electrons, and boom, you've got magnesium. All right, so going over the periodic table, you've got a couple of different things now. You know that the period that it's in is going to tell you how many energy levels. The group that it's in tells you how many valence electrons it's going to have. And we're going to focus for this last part on those valence electrons. This is going to be a little bit of a teaser until we get to ionic bonding. If you wanted both 2 different elements, the ones we just looked at, chlorine and magnesium, to be stable, they need to have octets. Would they be able to combine? We're going to take a look here on the Bohr diagrams, just kind of model this out. If you look at magnesium, again, because it's in the 3rd period, has 3 energy levels. 1, 2, and this is the 3rd one. Chlorine's in that same period, so it also has 3 energy levels. Same thing, 1, 2, 3. Chlorine has 7 valence electrons because it's in the 7th group. Magnesium has 2 valence electrons because it's in group 2. These things, what we could do is we could have a couple of them either lose electrons or gain electrons, so they can have ones that kind of shoot them out there, or some elements will just kind of suck them up if they're already just floating around. Take a look at magnesium. Magnesium is 2 valence electrons, so it has 2 options. It can either gain 6 electrons to get a full octet on its 3rd shell, or the other option it could do is it could just eject these 2 right here, and that means it goes back a level, and so it would have just these as its valence shell, but that's still stable. So with chlorine has 7 valence electrons, so it could either just gain 1 right here, I'm going to put an X where it could gain 1, or it could get rid of all these 7. When we're trying to determine what things are more likely to do, and again, more likely, not going to do every single time, they're more likely to do which of the options is easier. So when you look at magnesium, more likely that it's going to just drop those 2 right there. And in fact, that's what it normally does. So got these that have just kind of been dropped off, and they don't just disappear into nowhere. They're going to be floating out here somewhere. Chlorine, what it's more likely to do is to take up one of those electrons. So boom. So that took this one right here. So now what we do is we see that magnesium is happy, chlorine is happy, but there's a problem. This isn't exactly a good setup because we still have this one free floating electron somewhere. It, needs to do something. So usually, what we'll find out with bonding a little bit later is that for every magnesium, it can give one of its extra electrons to one chlorine, and then if there was another chlorine sitting out there somewhere, it would pick up the remainder. Okay, so it already has its 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 electrons sitting out there. Okay, again, this is what chlorine would look like normally, but it needs one more in this position. And remember, we had one that was sitting out here, so this electron could then get picked up out here. So what we would make with all this, I'm gonna erase here. What we would make with all this is Mg, it would have one Mg, and then 2 chlorines. Magnesium chloride, which we'll talk about all the naming and all that stuff again later. So I want to show you this one more time with the Lewis dot structures because, again, Lewis dot structures focus just on the valence electrons, and that's really what is in play here. So again, pretend for a second that we have magnesium, which has 2 valence electrons, and then we have chlorine, which has 1, 2, 3, 4, 5, 6, 7. Magnesium can transfer one of these over here, which makes chlorine happy because it's got an octet, but magnesium does not have an octet because it still has this one guy right here. So we would need another chlorine to transfer this electron over there. And then this Mg, I'm going to write it up above here. The Mg, since it lost 2 electrons, would become a positive 2 charge. We had a chlorine here that became a negative charge, and then a negative charge for this other chlorine because both of these gained 1 more electrons. So they have 1 more negative charge than they do positive charge. And this we're going to use when we get into ionic bonding here in a couple of days. So the final thing that you guys have in your notes is there are 6 different groups of elements to research. These are just ones that are ones of interest that show up pretty frequently, especially as you get deeper and deeper into chemistry. So group 1A is called the alkali metals. Group 2A is called the alkaline earth metals or alkaline earth metals, just depending on who you're talking to. The oxygen family is group 6A, and I bet you can probably guess why it's called the oxygen family. The halogens are group 7A, and group 8A are the noble gases. These ones are pretty interesting because they don't interact with anything else. That's kind of a good way to remember it. The nobles are too good to interact with the common elements, so we call them the noble gases, and again, they are all gases. And then finally, these ones, groups 3 through 12, the ones that are kind of in a tannish color, those ones are the transition metals, and there's a lot of interesting ones on there. We're not going to get into those in integrated sciences, but you guys will get higher levels of chemistry. You'll deal with them. So take a look at some of those different things. Again, knowing the octet rule is the most important thing out of today. And we are going to, again, use the periodic table. The groups are the columns, and those tell us how many valence electrons we have. The rows are called periods, and those are how many energy levels or shells or orbitals that you have. We're going to be looking at all this stuff. It's going to come in handy when we start bonding next. So if you have any questions, let me know.